So the basic strategy that we're going to use to figure out the reflection and the transmission coefficients will be as follows. So first what we will do is that we will express the initial wave function psi I. So in terms of energy eigenstates. And number two, since we know how the energy eigenstates evolve in time, we can evolve psi I. So we'll evolve psi I by evolving the energy eigenstates. Let's call them psi E. And then take the t goes to positive infinity limit. In that limit, we will identify how this wave function splits up into two components. One component would be the reflected component. Another component would be the transmitted component. And then we'll construct our transmission and reflection coefficient from that. So this is a general strategy. So what are the explicit steps? So the explicit steps would involve, the step one would be that solve for the energy eigenfunctions. Psi of E. So let's see how that works. So let's redraw our potential. So let's call this region 1 and call this region 2. So in region 1, we are solving for the wave function, which is going to be the solution to this equation, the time-independent Schrödinger equation. So in region 1, the solution we know is going to be given by psi of x. It'll have a constant e to the power I k1x plus b e to the power minus I k1x. So these are the two linearly independent solutions, because the time-independent Schrödinger equation is a second-order differential equation. And here, K1 is going to be given by m E. So this is essentially the kinetic energy, or the wave number, which is related to the momentum. So this is K1, and it's a positive number. And in region 2, the wave function is given by, it's given by a linear combination of two exponential functions. But the energy, the kinetic energy, is going to be different in this region. So K2 is going to be given by 2m. So what is the kinetic energy? It's E minus V naught. So this is the wave number associated with that kinetic energy. However, we know that when we combine these time independent solutions with the time dependent part, we'll see that this thing will give rise to a reflected part, and this thing will give rise to a part which is moving to the right, and this thing will give rise to a wave function which is moving to the left. But we know that in this region, we shouldn't have a wave function moving to the left. We can only expect a transmitted wave function. So there is nothing coming from that direction. So with that expectation in mind, what we can do is that we can set d to be 0. So our wave function in region 2 is going to be just the first term. So now that we have these two wave functions, we have to impose the continuity condition at the junction. So we want psi and psi prime to be continuous here, because our wave function, our potential is a finite step. So we expect from our differential equation that both psi and psi prime will be continuous. So from the condition that psi is continuous, we get the at x equals to 0. So psi, continuous at x equals to 0 means that we put x equals to 0 here and x equals to 0 here, and we set this one equal to this one. So from those two, from that condition, we get a plus b is equal to c. And from the constraint that psi prime has to be also continuous at x equals to 0, we get I times k1 a minus b is equal to I k2c. So which means that we have to take the derivative of this two expression. So that'll bring down I k1 here, and it'll bring down minus I k1 here, and it'll bring down I k2 here. So this is basically going to be our condition. So we can solve b and c in terms of a. Of course, we can only determine two of these constants. One of the constants, say a, will remain undetermined, and that's related to the fact that at the end of the day we want to normalize our resultant wave function, and that'll fix the value of a. So we can solve these two conditions. And if I solve those two conditions, it's a very easy thing to do. It's just you invert a 2 by 2 matrix, and then you get b is equal to k1 minus k2 divided by k1 plus k2 times a. And of course, if you want, we can put in the values of k1 and k2, and we know that that's going to give us square root of e times e minus v naught square root, and all the constants cancel out in the denominator and the numerator. So this times a. So this is our expression for b. And for c, we get 2k1 divided by k1 plus k2. Then we have a, and this is equal to, again, the other constants will cancel out from the numerator and the denominator. Right. So what we can now do is that we can express these two relationships, these two, expressions for the wave function as one equation. So to do that, we have to introduce something called the Heaviside step function. Heaviside was a Scottish mathematician and a physicist, and the modern form of Maxwell's equation that we know is actually due to Heaviside. He's the one who wrote the Maxwell's equation in a succinct form. So the Heaviside step function is this function. It's usually called theta of x, and it has the value of 1 if x is greater than 0, and it's 0 if x is less than 0. So that's why it's called a step function. So this has the following form. So this is x, this is 0, this is theta of x, and this is 1, and this is 0. So it is just like our potential, but this height is 1. So using the Heaviside step function, we can now express our energy eigenstate, or our energy, as A, the first term. So the first term has, we are factoring out EA, so e to the power I, kx, and then we have b over a. We're not going to write b in terms of k1, k2 right now, because then that'll just make it very clumsy. Then e to the minus I k1x. And this part of the wave function is non-zero and on the negative x-axis. So we multiplied by theta of minus x. So this guy is only 0 on this side. Only non-zero, it's 1 on this side. So that's where we have this wave function. In the region 2, we have c over a times e to the power, of course, multiplied by a, I k2 of x, and that's multiplied by theta of x. So this is our wave function. So we can also, of course, what we can do is that we know that we can express everything in terms of k1. So we know that we can relate k1 to k2. And if you do that, then what we can do is that we can rewrite the second term as e to the power I, and then we have k1 squared minus 2m v naught by h bar squared, and this whole thing should be square rooted times x. So this is k2, and then times theta of x. So this is going to be our energy eigenstate. And now what we can do is that we are labeling our energy in terms of the wave number. So we should really change this label, and we should use the label K1. So this is going to be the energy eigenstate. Okay, what is the next step? Step 2 is going to be, we're going to express our initial wave function psi I in terms of psi k1. So this, we are expressing it in terms of the energy eigenstate. So how do we do this? So remember that because k1 is it's a continuous variable, so it'll be an integral. So in principle, psi I would be the sum over I times some constant c of I, psi of I. Remember, this is what we discussed earlier in this lecture. is that any wave function can be expressed in terms of the energy eigenstates. But in this case, the index I is continuous. So in our case, psi I is going to be given by some integral over all of k. So let's call it k1. And the coefficient ci will be called a of k1. And then we have psi of k1 of x. This is going to be our psi I of x. So, so now we have to find out what a of k is. So to find a of k, we know how to find this. This is just given by the inner product of psi of k1 with psi of I. This is what we discussed earlier today in the lecture. So we have to compute what this integral is. So let's do that. So we have psi of k1, psi of I, the inner product of these two guys, and that will be given by, so psi of k1 has a. Let's take a to be real so that we don't have to star it. And then the first term, we have to write the integral sign. And then remember the first term, now the sign in the exponential is going to be reversed because psi of k is conjugated. So we'll have e to the power minus I k1x plus b over a. So sorry, we should really conjugate this as well. I'm going to make a particular choice of a soon, but for now let's just conjugate this. So e I k1x, so and then the heaviside theta function, step function, is real, so we are not going to conjugate that. And then we have to multiply this with psi I. And we have to integrate the whole thing over d of x. So this is our first term. And the second term is going to be, again, an integral from minus infinity to plus infinity. And then we will have c over a. And again, this will be conjugated. And the sign in k2 is going to be changed. And then there'll be psi I of x. So let me also put it here. And then there'll be theta of x, d of x. And then we can close all our brackets. So, so this is not a very hard integral to evaluate. So note that our initial state psi I has non-zero support only to the far left of the step of the potential. So if I go back to our picture, so remember that this is our potential, and our initial, let me go even further back. Our initial wave function has support only at the far left. So it has, by the time we get to the over here, this wave function is effectively died out. So that means that, this thing is zero when this thing is non-zero, right? Because this is only non-zero in the negative x-axis. This is only non-zero on the positive x-axis. So that means that the second term in this integral is 0. In these two terms, what we can observe is that, remember that this psi I has a momentum which is peaked, or so it has a wave number which is peaked at k0. So this is peaked at, So this is peaked at k0. Whereas this wave function, it's a conjugate of a wave function. It's conjugate of a wave function, which is of course peaked at minus k1, where k1 is a positive number. So in momentum space, we have essentially two wave functions which are peaked at very different values. And of course, by orthogonality of plane waves, their inner product is going to be 0. And therefore, we see that the second term is also going to be 0. So all we have now left is the first term. When we argued that this thing is going to be, this term is 0, this factor didn't matter. That's the puzzle that I'll leave for you guys to figure out. Okay, so now we have A of k1, which is just this thing. This is just this thing. So A of k1 is given by some normalization, which is, I'm going to call n or A or whatever. And then I can be very cavalier about overall normalizations in quantum mechanics. And we have e to the power minus I k1 x minus a e to the power I k0 x e to the power minus x squared by 2 del squared dx. So what have we done here? What we've done here is that we have used the fact that this thing is only non-zero in the negative x-axis, and this is also 1 on that part of the x-axis. Therefore, we just set the value of this to equal to 1. And then what we have here is this factor, and this factor is the first term in this exponent, and everything else is coming from this guy. This thing, there is no x dependence here, so we can factor that out. And if I do that, I get n e to the power I k1 a, and in the integral I have e to the power minus I k1, and then I have minus k0 times x e to the power minus x squared by 2 del squared d of x. So we can now go ahead and do this integral. This is just a complex Gaussian integral. And if I do that, then A of k1 is just given by delta by pi times e to the power I k1a e to the power minus k1 minus k0 squared del squared over 2. And what we have done is that we have chosen the normalization where this is 1 over square root of 2 pi. And what it allows us to do is to have this Gaussian on in wave number space or momentum space to be also normalized. This is step 2, and let's just recap. What we have done in step 2 is that we have expressed our initial wave function in terms of the energy eigenstates, and that involves figuring out what these coefficients are, and these coefficients are given by this Gaussian. Right. So now in step 3, we have to evolve our state. So This is going to be step 3. And what we want to do is that we want to find out what our initial state is at some arbitrary time in the future. So we are finding out psi of x of t, and that's going to be given by, so we know that, at time t equals to 0, it was given by this linear combination. But now we have a time dependence, and that time dependence is given by the usual exponential factor. And just remember that the exponential factor e is a function of k1. The energy is a function of k1. We can expand out our ak, and then what we will have is some normalization factors, delta by square root of pi, the whole thing will with square root, so this comes from a, and then we also get from psi, we got square root of 2 pi. We are using this normalization here for the value of a, and this normalization was fixed by trying to normalize this guy. And then we have the integral, and then we have e to the power minus I. Now remember what a is. So in the negative x-axis, where e is, what is the value of e? E is given by h bar squared k1 squared by 2m, but there is an h bar in the denominator, so the h bar squared just becomes one factor of h bar times t. So this is this factor. I've written it out explicitly. All right. And then what are the other factors? And then we have a factor of e to the power minus k naught squared del squared by 2. This comes from the expression for a, right? See, a has this term. So we are writing that. And then we have e to the power I k1a. So these are the common terms from both terms coming from this guy. So let's now write that out. What are the other factors? So we have two terms of the wave function from the region region 1. So there is this guy, and then remember we also had this guy. And in region 2, the value of the energy is different. There it's k1 squared minus 2m v naught by h bar squared, the whole thing being square rooted, times x. So this is the value of k2, sorry, not energy. And here we had this thing. So these are things we already know. Now let's figure out all the different terms. So let's consider the first term. So this guy. So it represents an incident Gaussian, and this can be shown after integration that it'll have the following form. So the integration is quite involved, and what I will do is that I will show you how that integral works in a separate video after this lecture. So what we are trying to do here is that we are trying to do this first integral. So this guy times this, all this stuff, all this junk, integrated over k. And multiplied by theta of minus x, and then with these coefficients. So you can show that, okay, well, let's look at it qualitatively. So this was basically that part of the energy eigenfunction, which was in region 2 and one of the exponents. So this is it. So if I do this integral, you can show that it has this form. It's theta, the Heaviside step function with the argument minus x. Then you have some normalization stuff, and then you have a normalization which is time dependent. So this time dependent normalization means that the height of the Gaussian changes as a function of time. It flattens, it actually becomes lower and lower. The height is, as t becomes larger, this factor becomes smaller and smaller. And then it has a Gaussian part, and the Gaussian part is saying that its position is given by minus a plus h bar k naught t over m whole squared, and that its width, its spread, is also a time-dependent object, so that it's as time goes, it spreads out, as well as its height becoming smaller and smaller. So that's given by this, the spreading out is given by this denominator. And then we have another factor, which is captures the momentum, average momentum. And of course, the average momentum has with it some information about its position as well, which is given by this factor. So this is basically a step function times a Gaussian, which is initially at position A with its wave number k naught, and is time dependent. So this Gaussian is centered at minus a plus h bar k naught t over m, right? So as time goes, this just becomes h bar k naught t over m, so which is a positive number. So which means that the Gaussian is going to be centered, far away from the negative x-axis. But because it's being multiplied by a theta function which is only non-zero on the negative x-axis, this means that there's not going to be any overlap between these two guys. So that means that as time goes to infinity, as t goes to infinity, this is going to be 0. So that's what we are trying to figure out. We are trying to figure out what the initial wave function will be at in the far future. And we just saw that the first term is not going to be contributing. So now let's look at the next term in the integral expression for psi I. Now let's look at the coefficient, this coefficient. So it's a function of k1, as we saw before. But the whole thing is being multiplied, so over here, by a of k1. Now, what is a of k1? We saw that a of k1 is also a Gaussian. And we saw that, the delta was the spread of the of the original Gaussian in position space, and we had discussed that. We had stated that that's actually quite large. So because this delta now here is the numerator in the argument of the exponent, that means that this guy is very, very sharply peaked around k0, right? So what we can do is that this means that if I look at this integral, if I look at this second term, because this Gaussian is very sharply peaked around k0, what we can do is that we can set k1 to be k0 in this coefficient. In other words, we can consider this to be a constant. There should be k1, right? So we can put k1 to k0 and consider this to be a constant. So we can pull this out of the integral. So we can pull this thing also out of the integral because this doesn't depend on k1. So once we pull these two things out of the integral, our integral then becomes e to the power minus I h bar k1 squared t over 2m, then e to the power minus k1 minus k0 squared del squared divided by 2 e to the power minus I k1 x minus a delta of k1. Of course, what we can do now is that we can let k1 go to minus k1. So what that does is that we pick up a minus sign here, and these two signs become, they're interchanged, but then we can absorb this minus sign and then change back the limits of the integral from minus infinity to plus infinity. But what it also does is that over here, it changes the sign to a plus sign here. It changes this to a minus sign here, which we can then, factor out, and this all becomes plus signs, and this is what we get. So we can now compare this with the previous integral that we did, and what we find out is that it represents a Gaussian which is moving to the left with negative momentum h bar k naught, and which is originally peaked at x equals to a. So we can write this guy as the reflected wave function. So the psi r is going to be the step function which is with the argument minus x, and a Gaussian which is originally peaked at a, and its momentum is negative, and then times b times a, whose value is evaluated at k0. Now as t goes to infinity, we can set this thing to 1, and so the Gaussian is then, its position is going to be, it was a minus h bar k naught t by m, so this will be given by minus h bar k naught t over m, and thus we see that the Gaussian is going to be on the negative x-axis. So that we have figured out what the reflected coefficient is, reflected wave function is, we can then work out what r is. R is going to be just psi of r, this thing, and I think this is going to be squared, yeah, with E0 given by right. So to find the transmission coefficient, we can evaluate this last term, but we're not going to do that. Instead, what we're going to do is that we're going to use the fact that probability is conserved. So R plus T is 1. And because we figured out what R is, we can find out what T is. So T turns out to be. So note that we have E greater than V0, but R is not equals to 0. So this means that, unlike in classical physics, in quantum mechanics, whenever we have a particle which has energy greater than the potential energy of a barrier, there will be a non-zero chance probability that it'll get reflected back.